Hello, pre-calculus students, calculus students, and especially general seekers of truth. This video and the next several videos are really for you who love truth, because we're getting to the beginnings of some higher level stuff here. So before you watch this video, make sure that you understand the Tower of Hanoi game. If you don't know what that is and how that works, you need to go back and look at the previous work or look at some of the handouts from earlier in the class, because you need to be able to understand what is going on up to this point here. Right? So what we want to do now is to find if there is a pattern between n and a sub n. N is the number of discs in the Tower of Hanoi game, and A sub n is the minimum number of moves necessary to solve the game. And we can see that there is a bit of a pattern emerging here. And if you see this, you can see that to solve for one disc, it's very obvious. You just pick up the disc and move it to the final location, and that's just one move. To solve for two discs, 3 here is really just 2 times 1 plus 1. 7 here is just 2 times 3 times the previous number of moves plus 1. And once again, what I'm doing here is recapping what you already know from the previous videos. 15 is really 2 times the previous number of moves, 2 times 7 plus 1. And of course 31 is 2 times 15 plus 1. So however many discs there are, if we want to figure out the minimum number of moves, we look at the previous minimum number of moves, multiply that by 2, and then add 1 to it. And we can trace this process back all the way back to one disc. Now, if you notice here, when n equals 1, we don't need to define it in terms of the previous, because n equals 1 here is the starting case. Okay, so it's the starting point. So we don't need to go back any further. So the recursive definition for this Tower of Hanoi sequence is fairly simple. For any a sub n, any minimum number of moves, if you want to know what is the minimum number of moves for n discs, you take the minimum number of moves for n minus 1 disc, multiply that by 2, just as what we're doing here, and then adding 1 to it. Now this only applies when n is 2 or greater, so we should clarify that this is for n greater than or equal to 2. So we remember that we need a starting point somewhere, and so our starting point for the Tower of Hanoi must be at 1, so a sub 1 is equal to 1. So this is the recursive sequence that describes the minimum number of moves necessary to solve the Tower of Hanoi with n number of discs. Now let's move on and see if we can find an explicit formula, or at least figure out the beginnings of an explicit formula. And what you'll notice here is that 1, 3, 7, or what I notice here is that 1, 3, 7, 15, 31, they're very, very close to powers of 2. So 3 is really close to 4. Right? 3 is really just 4 minus 1. 7 here is really just 8 minus 1. 15 is 16 minus 1. And 31 is really just 32 minus 1. And 1 is, well, 2 minus 1. So if we try to find some sort of pattern here, we can express this in terms of powers of 2. So this is really 2 to the first minus 1. This is 2 to the second minus 1. This is really 2 to the third minus 1. 16 is 2 to the 4th minus 1. And of course, 32 is 2 to the 5th. And we have minus 1 here. So the explicit formula, and this looks like a sub n is equal to 2 to the nth minus 1. And I'm going to put a question mark here because we haven't quite proven this yet. This is a good conjecture, and this we can go on, we can go on listing out these forever, but the truth is we haven't really proved this yet. Just because the pattern looks good doesn't necessarily mean it's true. It's probably true, but in mathematics there are many examples of conjectures and hypotheses that seem true for a very, very long time, for very, very large numbers, but isn't true for some, but eventually someone finds a counterexample. So we think that this is true, but we don't know, right? So maybe at like n equals 50, the explicit formula will suddenly be different. We don't quite know that for sure right now. So we're going to need some way in order to prove that such a claim is true. So that's what we're going to work on in the next video, where we expand on this and show how do we go from the recursive formula to the explicit formula and prove that such a statement is true.